Hello, my name is Nikita Oro, card matrix BI25110522. This is assignment 1 CAO. So for the first question, consider a computer with the following characteristics. Total of 256 kilobytes of main memory, a block size of 32 bytes, and a cache size of 64 kilobytes. So for A, thing that we should emphasize on is the given corresponding tag, cache, line address, and word value for a direct map cache. So two addresses are given. The first one is 3223A and 222.220E1. We should convert both of these two addresses to hexadecimal for the first step. As you can see, the ones that I've given in my answer sheet, we get the binary code and you'll get 20 bits sequence out from these addresses. The 322A is 0011001000100011111010. And as for 220E1 is 0010001000110001. 20-bit sequence. Now let's convert it to 18-bit sequence so we can apply the catch field. Tag is for the leftmost two side. The line is the middle 11 and the word is the rightmost 5 plus digits. For the fourth step, binary to hexadecimal, tag 11, the tag turns to 3, and for the second address is 2. For line, we should group to 3 groups of 4, starting from the right side. So the line will get 111, and for the second address, we'll get 01. And for the word that we'll get for the first address is 1A, and the second one is 10. And right now, let's jump into question 1B. There were 3 addresses that is given, which is 01336. For second one is 21736. Third one is 11736. First step, we should change all 3 addresses to 18-bit binary. As you can see, the first two is the tag, the middle one is line, and the last 5 is word. Second step is to find which address that will be stored in the same line in the cache. Out of these 3, which one will be stored in the same line? First one is 099, second one is 0B9, third one is 0B9 as well. So in conclusion, third step, address 2, 21736 and address 3, 11736 will be stored in the same line in the cache. For C, 11221 and 1FEFF, given tag and offset, in other words word, for a fully associated cache. First step, word still remains 5-bit because the block size remains 32 bytes, which converts to 2 to the power 5, which equals to 32. For tag, since the memory address is 18 bits, the tag is 18 minus 5, and that equals to 13 bits. That is for tag. Instead of splitting instead the split being tag 2, line 11, word 5, we do the split in line 13 and word 5 because it is a fully associated cache. Continuing from question 1C, the first address 11221, hexa to binary, as I have given in my answer sheet. As you can see there, that is the binary that I've got. I convert the 20 bits to 18 bits, excluding the first two, the leftmost first two, splitting the 13 and 15. The first 13 digits are tag, and the last 5 is words. For the fifth step, we want to find out the tag and the offset, the hexadecimal value for this to address. The first value of tag I've got is 0891, and the offset is 01. And the second address of tag is 0FF7, and the offset is 1F. Up next is question 1D. Now this includes the two-way set associative mapping. Total address bits are 18 bits from the 256 kilobytes. That equals to 2 to the power of 18 bytes. So the offset bits are 5 bits from 32 bytes. That equals to 2 to the power of 5. Set index bits. The total catch line is 64 kilobytes over 32 bytes. That gets you 2048 lines. Number of sets, you take the 2048 lines over 2, which means 2 ways, equals to 1024 lines. That's for number of sets. So in conclusion, 2 to the power of 10 is equals to 1024. We need 10 bits for the set index. So the tag bits, the two ways, the 18 total minus 10 set minus 5 offset. That gives you 3 bits. That's for tag. So now we know tag is 3. Convert hexadecimal address to 18 bits binary with applying the split of 3, 10, and 5. Address 12222, you get the hexa binary that I've given there, and you split it with the split that we're going to use, the 3, 10, 5. First one, the tag, the 3 bits, we get 2 hexadecimal. The catch set is 111, and the offset is 02. For the second address, the tag, the 3 bits is 6. The catch set is 227, and for the offset, the last 5 bits is 02. Jumping into question 2 for assignment 1. Number of lines are 16. It's 1 to F, which means 0 to 15. The block size, the diagram shows each line is 4 words wide. Total catch size is 16 lines times 4 word slash lines, which equals to 64 words. So the 2A, find out the width from the mapping question. The word offset bits is 4 words per block. We need log 2 times 4. That gives you 2 bits. For line index, since there is 16 lines in the catch, we need log 2 times 16. That gives you 4 bits to identify the lines. Tag bits, depending on the address size, usually given in the text, which we got in here in the figure 1. That is for tag bits. B, identify the length of the main address. The total address is 12 bits. Line is 4 bits. Word is 2 bits. So the way we get the tag bits, the one that we have to calculate is 12 minus the line plus the word, which is 12 minus 4 plus 2, which gives you 6 bits. That's for tag bits. C, how many blocks is in the memory? To find the number of blocks, we have to apply the total addressable memory over size of one block. That's the formula that we're going to use. Total memory location, since address is 12 bits, they are 2 to the power of 12, which gives us 4,996 words in total. The block size, each block has 4 words based on figure 1. The calculation for this is 4,096 words over 4 words slash blocks. That gives you 1,024 words. And for 2D, the direct memory mapping, we have line 4 bits and word has 5 bits. Binary has 12 bits, as I've given in my answer sheet. The split is 6, 4, and 2. So the line bits 0001 is equals to 1. So the maps leads to catch line 1. For the second binary, the maps leads to catch line 14E. For question 2E, the two-way set associative. Set is 3 bits, word is 2 bits. The total line is 16. Line per set is 2. So since it's a two-way set associative, the total set is 16 over 2, which gives us 8 set. Not 8 line, but 8 set. The bits needed for set is log 2 times 8, which gives us 3 bits. Now the split, the new split for this question is 732. So the tag is 7, the set is 3, and the word is 2. For the first step, for the first address is 344. The binary that I got in the answer sheet that I've given is there. So right now we want to look for the set bits, which is in the middle, and I've gotten 1. So maps to catch set 1. For the second address, 3BB, it maps to catch set 6. So F, how does the set associative mapping handle the missed data? We have 2 ways. First one is fetch from main memory. The CPU recognizes the required data is not in the assigned set. It then accesses the main memory to retrieve the entire block containing the address needed. So the address needed is required data and assigned set. The required data is addressed from 344, for example, and the assigned set for 344 is set 1 based on part E. For 2, replacement process is for the second way. Once the block is fetched, the catch controller must decide where to put it within the 2 lines of set 1. So for the last question, 3A, how many bits are required for PC, AC, and IR, the program counter, the accumulator, and the instruction register? PC is 11 minus 4 plus 1, which gives us 8 bits. AC is used to store data and perform arithmetics. The integer format shows that the data occupies from 0 to 11. The IR must hold the entire instruction, both 4 bits opcode and the 8-bit address, while it is being decided. So for question B, we have 10 steps, 5 fetch and cycles. So it's 0101 for the first fetch and cycle. As you can see, the AC changes from 00 to 02. IR remains the same. For step 3, the changes are AR, which we can see the IR that we have gotten is 812. That leads us to 01. 01 means load AC from memory. And with that being said, 6 to 7 maintains the same, 05 and 05. But the IR changes from 313 to 112. And then the step 7 to 8 is 04 and 04. The PC remains the same, but 112 it subtract. The AC goes from 005 to 003, whereas the IR changes from 112 to 410. And now for step 9 to 10 is 05 and 05 for PC, 003 to 001, which subtracts 002. IR maintains the same. That is all for question 3, assignment 1. Thank you.